it's regulated. So antidiuretic hormone is the hormone that controls the physiology. Generally, if you have some dehydration, for whatever reason, the osmolarity in your blood's getting worse. You have to conserve fluid to correct that. And so what this antidiuretic hormone does is anti-diuresis you. It reduces the amount of urine that you lose. The volume of urine decreases. That fluid that's retained, that's not lost in your urine, is returned to the cardiovascular compartment, and that will help dilute the osmotic particles in your bloodstream, and that will restore osmolarity. And usually the osmolarity of the blood should be no greater than about 290 milliosmoles per liter. You start to get up to that end, the antidiuretic hormone is released, and again, to try to compensate for any potential hyperosmolarity that might develop. All right, this is how it works generally. Okay, we got these osmolar receptors. These osmolar receptors will constantly monitor the osmolarity of the blood. When they detect hyperosmolar conditions or conditions that are becoming hyperosmolar, antidiuretic hormone is going to be released. The antidiuretic hormone is going to operate on the distal segments of the kidney nephron. Remember, it's the distal segments of the kidney nephron that primarily refines things, regulates things. The same thing is true with the ADH. ADH operates on the distal segments of the nephrons. There's our glomerulus. There's some of our proximal segments. Here's our distal segments. It's going to operate mostly on the connecting tubules and the conducting ducts. And it'll change the permeability of these parts of the nephron. It will increase their permeability to fluids, water. As a result, when urine passes through the nephron, when it gets to this collecting duct, the fluid's going to be extracted from the tubule. And that fluid that's extracted from the tubule is going to be returned to the cardiovascular compartment. So the more permeable to water this tubule is, the more opportunity fluid can be resorbed from it. That fluid that's resorbed is returned to the cardiovascular compartment. Okay, again, here's the sequence of events. We got a deficit in water. That's going to increase the extracellular osmolarity. That's going to stimulate the osmolar receptors. That's going to cause ADH secretion. ADH is produced where? Hypothalamus, which nucleus?
Supraoptic.
The supraoptic nucleus, and it's released where?
Posterior pituitary.
Posterior pituitary gland. So you got these axons that are running from that nucleus, terminating in the posterior pituitary gland, release ADH, picked up from the posterior pituitary gland by rich vascular supply, it's going to be distributed to the plasma. That's going to operate on those distal segments. Permeability to the water is going to increase. It allows for fluid resorption, and you'll get a decrease in the amount of fluid that's lost in the urine. So when you're producing ADH, you would expect what concentration of urine? High or low?
Higher.
Concentration should be high because you are pulling fluids away from the urine, and whatever remains is going to be concentrated. Okay? What's the volume going to be? Volume of urine, low, relatively low. So you should develop highly concentrated, low volumes of urine when ADH is being produced. And that makes sense. That's physiologically compatible with a hyperosmolar state. All right, any questions on that part? So we talked about that last time. All right, let's have a look and see exactly how this antidiuretic hormone works. Okay, so I mentioned before that the antidiuretic hormone principally operates on the distal segments of the nephron. That's where a lot of fluid resorption will occur, and that's going to refine and change the concentration of urine, ultimately determine the concentration of the urine. All right, so we have two depictions of the nephron here. We have one in the presence of ADH, the other is in the absence of ADH. So let's take a look at the operation of the nephron in the absence of ADH. So you're not producing antidiuretic hormone. That should result in a state of diuresis. You should be losing fluids. If you're be diuresed in the absence of anti-diuretic hormones. So let's see what happens. So here's a representation of the glomerulus up here in the cortex. Okay, we're going to produce this ultrafiltrate. It's going to empty into the proximal convoluted tubule. Then it's going to run through this loop of Henle. Now, as the ultrafiltrate runs through the loop of Henle, a lot of this water, this fluid in the ultrafiltrate is going to be resorbed. That's because the medulla here is hypertonic. There's a lot of osmotically active particles, and it's going to tend to pull fluid back out of the ultrafiltrate, and it'll return it to the interstitium and probably the cardiovascular compartment. As the ultrafiltrate goes back up again, it pulls back some fluid, and so it becomes dilute again. By the time it reaches the distal convoluted tubule, the ultrafiltrate's dilute again. If there is no change in the permeability of the walls of these distal segments, then water is going to flow through the connecting tubule into the collecting duct, and it's going to flow right out into the urine, right out into the bladder. And that's because the walls of these tubules are impermeable to water. So there's no further opportunity for water to be pulled out by the hypertonicity of the medulla. And so the fluid's going to go right straight down into the calyces of the kidney, ultimately wind up in the bladder. Okay. And as a result, you have very dilute, large volume, very dilute urine. Okay, what happens in the presence of anti-diuretic hormone? Well, anti-diuretic hormones principally going to affect the permeability of water of this collecting tubule. So let's see what happens. So again, we've got our glomerulus producing a lot of this ultrafiltrate. Again, it goes to the loop of Henle, there's some concentration. The ultrafiltrate comes up again, and it gains a lot more fluid and becomes dilute again. Okay, nothing different here. Next, what happens, however, is the fluid's going to go through this connecting tubule. The connecting tubule, then onto the collecting duct. Now, this is occurring now in the presence of anti-diuretic hormone, and what the ADH has done is increase the permeability of the walls of all of these distal segments to water. So now as the ultrafiltrate goes through here, and especially as it goes down the medulla, the hypertonicity of the medulla is going to be able to pull the fluid right out because the walls of this collecting duct are now permeable to water. And now there's an opportunity for the hypertonicity of the medulla to pull this fluid out. Fluid will enter the medulla, and it's going to be returned to the cardiovascular compartment. The result is you have very low volume, high concentration of urine, and that's going to enter the bladder. So these are where the changes occur. They occur in this connecting tubule and the collecting duct. All of those parts of the nephron are what we call the distal segments. Those distal segments are influenced by ADH. ADH can change the permeability of their walls to water. Any questions on this? All right, let's have a closer look at how ADH works. Okay, we're going to take a look at some of the biochemistry behind how ADH achieves a change in the permeability of these distal segments of the water. Okay, so let's take a look at a representation of the epithelium of the distal segments and some of the vascularity. So here we have a representation right here of the distal collecting tubule. We have the lumen right over here. There's the epithelium right there. Got these epithelial cells that are lining the collecting duct of the nephron. Okay. Over here we have some what looks to be part of the vascular network that's going to occur in association with a lot of these tubules, peritubular vascularity. There's a little blood vessel right there. Okay, let's consider what happens normally, perhaps in the absence of ADH. Okay, got no ADH. So the permeability of the collecting tubule without ADH, is it going to be permeable to water or not?
No.
It's going to be relatively impermeable to water. Water won't be able to flow easily through the wall of that collecting tubule without ADH present. Okay, well, let's consider what we got going on in this epithelial cell. So here's the apical membrane of the epithelial cell. There's the base membrane. cell, basal membrane, apical membrane. Within the apical membrane of the epithelial cell, we have these little pores. These pores almost exclusively conduct water. These pores are called aquaporins. They're aquaporin molecules that are almost solely for the purpose of conducting water. Okay, so maybe under conditions where we don't have a lot of ADH, you'll find that these aquaporin pores are present in the apical membrane, and they allow some water to come through, maybe not a lot, but some water to come through. This water will traverse the cytoplasm of this epithelial cell, and it'll end up going out the basal membrane, and eventually will be deposited back into the vasculature. And so maybe without a lot of ADH present, you have some, but maybe not a lot of water being resorbed back into the vascular compartment. But now let's take a condition where we've got a lot of ADH present. Antidiuretic hormones should make these epithelial cells more permeable to water. Okay, so ADH is going to be distributed hematogenously, so it's going to get into the vascular compartment. First thing ADH is going to do is dock with its receptor. There's something called a vasopressin receptor here. Vasopressin is another name for ADH. ADH docks with the vasopressin receptor. This receptor is a G-coupled receptor, so there's a G protein right there. G protein becomes activated. The G protein in turn will activate an enzyme called adenylate cyclase. Okay? Adenylate cyclase, you know, once activated, produces cyclic AMP. ATP is converted to cyclic AMP. Okay? Cyclic AMP in turn will operate on a cyclic AMP dependent protein kinase called protein kinase A. Protein kinase A. What does protein kinase A do? It just phosphorylates proteins. Once it's activated, it's going to phosphorylate a subset of proteins in the cell. One of the proteins it will phosphorylate are proteins in this little vesicle that you find just below the apical membrane of the epithelial cell. Excuse me. This little vesicle contains a lot of aquaporin. The aquaporin is just sitting in the vesicle. The aquaporin is not doing anything. It's just sitting in the vesicle. It's part of the vesicle, but it's not doing anything. However, when the protein kinase A phosphorylates the vesicle proteins, this vesicle will fuse with the apical membrane of this epithelial cell, and it will deposit in the apical membrane additional aquaporin pores. And when these additional aquaporin pores are deposited in the apical membrane, now more fluid can come through here and go out the basal membrane and end up in the vascular compartment again. What have we done? By causing this vesicle to fuse with the apical membranes, we've increased the density of those aquaporin pores, and we've increased the permeability of water to the cell. The cells increase its permeability to water. In doing so, now as the urine comes down here, we can extract more fluid from it, concentrating the urine, again reducing the overall volume of urine produced. Yes?
So the urine is passing by these aquaporin receptors, and since they're now more permeable, it sucks in the water.
There's a greater density of aquaporin pores.
And
So
then that is what brings the water in? Back
that
into
will
the
increase
cell?
the water absorption. The increase in density of aquaporin. Okay, any other questions on this slide?
I have a silly one, just a confirmation. The aquaporins are the AQPs that we have in the note packet, right?
What?
The AQPs, we have them in the note packet. I just wanna confirm that that's the
Oh,
aquaporins.
it's aquaporin.
I just wanted to confirm.
Yes.
Okay, thank you.
I have the same question. There's no difference between AQP and AQP2, right?
Yeah, there are different isoforms of aquaporin.
They're different.
Yeah, so you see you've got aquaporin 2 over here, aquaporin 3 over here. The gene expressions are different. These might be constitutively expressed, whereas these might be variably expressed. The density may also be variable based on whether the vesicle fuses with the apical membrane.
But the function is the same.
The basic function is
Yeah.
the same. They still conduct water. The important thing to know, however, is that the density of aquaporin is changing the apical membrane, not necessarily the basal membrane. Okay, anything else on that? All right. So let's mention a few other things. So I have said a couple of times now, the principal function of ADH is to control osmolarity. Now, inadvertently though, ADH could increase the volume of the cardiovascular compartment. After all, if you're retaining fluid to reduce osmolarity, you can expand the cardiovascular volume. Now, that may not be its principal function, but it is one of its minor functions. There's another hormone that principally controls cardiovascular volume. We'll get to that. But as a result of that minor function, ADH secretion can also be affected by some other factors. For example, if there's a low mean arterial pressure, that's the MAP at the bottom of page 4, MAP stands for mean arterial pressure. If there's a decrease in mean arterial pressure, there are going to be a series of changes. One of those changes might include additional elaboration of ADH. ADH will help expand the cardiovascular volume by retaining fluid. That's not its principal function, but it is a factor that might influence the amount of ADH produced. Also, angiotensin II, which is a pressor agent, meaning it increases blood pressure. The production of angiotensin II, which is primarily produced so that we can increase blood pressure for the perfusion benefits of the kidneys, that may also slightly influence the production of ADH. And ADH not only reduce osmolarity, but it will expand cardiovascular volume. Okay, any questions on that? All right, let's talk about some different hormonal derangements in ADH. Well, sometimes, yes.
Before you get too far forward, there's a ton of, in the notepad, there's a ton of abbreviations under aquaporins.
Sure.
We weren't just talking about.
Oh, those are abbreviations referring to different segments of the nephron.
Okay.
So things like ATL, ascending thin, segment of the loop of Henle. And we've got
I'm sorry, you said ATL is ascending loop of Henle?
Yeah, they're actually on this, on one of the slides.
Oh, they
I
are?
believe they're on one of the slides.
The abbreviation?
PT is the proximal, would be proximal tubule. DTL, distal tubule. Okay. And again, what I really would like you to know is proximal segments, distal segments. I've talked a lot about the distal convoluted tubule. I've talked a lot about the connecting tubule and the collecting duct. And all these other segments, I'm not saying they're not important, but since we didn't dwell on some of their functions, you know,
Thank you.
it would be, I think, reasonable for you to kind of familiar yourself with the nephron, but specific questions about, say, the loop of Henle, you know, other than maybe it keeps down, goes down into the medulla and comes up again. These thin and thick segments, we can spend a long time on those. And I don't think that would serve you well.
I found the slide with that.
Great.
Like the decoding, thank you.
Which slide is that? That's
Which slide is it?
It's, I think slide 8.
Okay. Thanks.
It's called the distal segment, yeah.
Yeah. Okay. Anything else? All right, so let's take a look at those hormonal abnormalities. So in some individuals, there's going to be too much ADH produced. Some individuals will be too little ADH produced. Let's take a look at some examples where we have too little ADH produced. That's called ADH deficiency, vasopressin deficiency. Without antidiuretic hormone, what do you think some of the presenting features are gonna be? Deficiency in ADH. Someone's not producing a lot of ADH. You urinate a lot, so polyuria, they're produced by polyuria. Okay? Is the polyuria, is that gonna be concentrated urine? No. Be dilute, lots of urine. Okay, now, if you're not making ADH and you're polyuric, you're losing a lot of dilute urine, what do you think that's gonna do to the osmolarity of the blood? Yes, it's gonna start to concentrate. You have concentrated blood, hyperosmolarity, with a lot of dilute urine. Those are not physiologically compatible. If you have concentrated blood, you should be concentrating that urine, so you're preserving what fluids you have. And so that condition, that is not physiologically compatible. Person's not making enough ADH and they're losing a lot of dilute urine. We call that condition diabetes insipidus. Diabetes insipidus. The word insipid means dilute or not concentrated. It refers to the urine. Diabetes insipidus is characterized by the production of voluminous, low concentrated urine. Now, if a person has a high osmolarity in the blood, something's wrong. That shouldn't happen. Now, just a couple of things to be aware of. When we measure osmolarity in blood, we're not necessarily measuring all of the different particles in the bloodstream that contribute to the osmolarity. Very often, we're just going to look at sodium. Sodium is a cation that's primarily extracellular. And so very often we use that as a marker for osmolarity. A person with diabetes insipidus should have a higher than normal concentration of sodium in their bloodstream. And that's called what?
Hypernatremia. Hypernatremia?
Hypernatremia. Hypernatremia. So someone with hypernatremia, get a lot of voluminous urine, that's not compatible. That's not physiologically compatible. Something's wrong. Okay, so that condition is called diabetes insipidus. Very often, diabetes insipidus will follow a head injury. A typical history you'll get, someone falls off a ladder, hits the back of their head. They just might damage the axons of the neurons that travel from those hypothalamic nuclei and terminate in the posterior pituitary gland. The shear stress of change, quick change in velocity, that might cause enough shear stress to damage those axons, and they may not be producing ADH. And so typically the history you get, there's some sort of head trauma. And following the head trauma, all of a sudden they're urinating a lot. They're also going to be drinking a lot, polydipsia. They're going to try to compensate. They're going to drink a lot, they urinate a lot, yet despite all that, they're going to have hypernatremia. That's going to be the typical history you get from someone like that. Okay, any questions on that?
Is diabetes insipidus something that becomes permanent, or is it just like capacity, you think?
Diabetes insipidus, with that kind of history, the head injury, it's usually permanent. So we have to treat it with another hormone. Yeah, desmopressin. Yeah.
Is there an alternative, like, situation where there's too much ADH?
Yes, it's called the syndrome of inappropriate ADH secretion. Syndrome of inappropriate ADH secretion.
You just made that up.
Well, you asked me.
It's just a word, right?
Be careful what you ask. This is something that could be related to the hypothalamus. It could be related to a problem with the hypothalamus. The hypothalamus is just making too much of this ADH. Naturally, if you're making too much ADH, what are the presenting features going to be?
Probably less urine?
Less urine. Concentrated urine.
Maybe swelling?
What's that? Less concentrated blood, so hyponatremia. Yep, those are all features of SIADH, syndrome of inappropriate ADH secretion. Now again, this problem could be related to the hypothalamus, or more likely it is going to be something called a paraneoplastic syndrome. This is a type of hormonal derangement that occurs in association with cancers, very often lung cancers. We're going to talk about cancer. There's a derangement in the gene expression of those cells, and sometimes a cancer cell will inadvertently activate a gene it's not supposed to activate. One of those genes might be the gene that encodes for ADH, and now all of a sudden you're producing a lot of ADH. And this ADH is going to be produced without any consideration of the osmolarity of the blood. It's going to be autonomously produced, and that generally will cause SIADH. That's one of the more likely causes of SIADH. Okay. Any questions on that? So if you had an exam question, and I was giving you some lab data, a person's sodium level is very, very low, and I told you that the urine is concentrated, low volumes, I asked you to choose. What's causing that? Is that diabetes insipidus or is that SIADH? Which one are you going to choose? SIADH. And that would be a typical question I'd ask. All right. All right, so let's take a look at regulation of cardiovascular volumes. Any questions about osmolarity? All right, let's talk about cardiovascular volume. What controls cardiovascular volume? This is the, yes.
Can this lead to blood clotting? Like if you have increased osmolarity in the blood, can it lead to, or I mean, increased concentration, right? Will it lead to like clotting in the blood?
If the person's losing more fluid, then presumably not only the electrolyte's going to concentrate, but also the formed elements are going to concentrate. That tends to make the blood more viscous, and it can become stagnant, at least more stagnant. Maybe even lose laminar flow. Okay, anything else? All right, let's take a look at what controls cardiovascular volume. So, we talked about what controls osmolarity. We talked about, we're going to talk about what controls volume. So, the principal controlling mechanism of volume is going to be the renin, angiotensin, aldosterone axis. Now, we've already mentioned this a few times in the past. This is something that is controlled by the kidney. It's controlled principally by the juxtaglomerular complex in the kidney. Let's see how this works overall. The RA axis is primarily designed to maintain perfusion to the kidneys. So the kidneys, they have to receive about 20% of your cardiac output to be efficient. You're going to filter about 20% of your cardiac output. In order to work, they have to get blood flow, otherwise they can't filter anything. And so you have to maintain blood flow to the kidneys. That's a priority. Okay. Well, the RA axis helps the kidneys achieve that. All right, so let's take a look at what would happen if perfusion to the kidneys dropped a little. Okay, well, the kidneys aren't going to like that. The kidneys are going to notice there's a decrease in glomerular filtration rate. And ultimately, that little complex, that juxtaglomerular complex that's kind of situated between the distal convoluted tubule and the glomerulus, it's going to detect that. And it's going to respond by elaborating this, renin. Renin is a protease. It's going to be released right in the bloodstream.
Thank you.
And the renin is going to operate on this precursor molecule in the plasma. It's called angiotensinogen. And it's going to cleave the angiotensinogen into angiotensin 1. Now, angiotensin 1 has some functions, but none of which are going to interest us today. What's more important is that angiotensin 1 is going to be converted to angiotensin 2. And this is going to occur via the action of an enzyme called angiotensin converting enzyme, or ACE for short. And ACE is principally concentrated in what tissue? Lungs. So this angiotensin 1 goes through the pulmonary vasculature, and it's gonna get operated on by this angiotensin converting enzyme. This angiotensin converting enzyme is gonna convert it to angiotensin 2. Now, angiotensin 2 has a number of biological effects that we are interested in. Angiotensin 2 is gonna try to restore perfusion pressure to the kidneys two ways. Firstly, it's gonna cause vasoconstriction. Okay? Vasoconstriction is the general overall effect, and when you vasoconstrict, you increase total peripheral resistance, and that's gonna be one of the major factors in Ohm's law that dictates blood pressure. Blood pressure equals cardiac output times total peripheral resistance. TPR goes up, blood pressure goes up. And that will contribute to feedback in the production of renin. But that's not the only thing that angiotensin 2 is going to do. Excuse me. Angiotensin 2 is also going to operate on the cortex of the adrenal gland, specifically the zona glomerulosa. Zona glomerulosa, in response, will release this, aldosterone. Aldosterone is a steroid. It's called a mineralocorticoid. Its function is to operate on the distal segments of the nephron to increase the absorption of sodium and increase the excretion of potassium. So, this is operating specifically in the distal convoluted tubule. Distal convoluted tubule has this little sodium-potassium exchanger. It's going to increase the activity of that sodium-potassium exchanger. It's going to absorb more sodium. It's going to get rid of more potassium. The sodium that's retained is going to result in more fluid being retained. So you're retaining sodium and fluid back to the cardiovascular compartment. That's going to expand the cardiovascular volume. And that ultimately is going to increase cardiac output. Okay, cardiac output increases. That's another major factor of Ohm's law. You've got cardiac output increasing. You've got TPR increasing. Both major factors, Ohm's law. That's going to increase blood pressure, and that will feedback and inhibit the production of more renin. Now, we've increased the blood pressure here, and that is going to restore perfusion pressure to the kidneys. At the same time, we've also expanded the cardiovascular volume. That's the principal function of things like aldosterone. Aldosterone is a hormone that principally controls cardiovascular volume. Now, can aldosterone also affect osmolarity? Yes, under special circumstances. Is that its principal function? No. So, I notice a lot of authors in textbooks will report that yes, aldosterone controls volume and osmolarity. Volume, yes. Osmolarity is not its principal function. It is possible that if you have hyperaldosteronemia, you're producing a lot of aldosterone, you overly absorb a lot of sodium. That can cause hypernatremia if the person is not able to access fluids and drink. If they are able to access fluids and drink, you're not going to see any change in sodium concentration. Okay. Questions here?
So, is it more controlled in the blood? Like, is it doing this because the infusion rate at nephron is not high enough, so it's increase the pressure, so it increases the pressure?
Right. It's ultimately determined by the amount of filtrate passing through the distal convoluted tubule and the amount of sodium chloride passing. But that also depends on perfusion of the kidneys, which is going to be related to perfusion pressure. Anything else? Okay, so let's have a look at where aldosterone comes from. Again, this is the hormone we want to talk a little more about. Principal function to control cardiovascular volume. It comes from this organ. This is the suprarenal gland. It's also known as the adrenal gland. You know there are two primary parts of the adrenal gland. You've got the cortex, there's the cortex, and there's the second part, the medulla. The cortex has the function of producing a lot of steroid-based hormones. Steroids are fatty. Fat looks yellow, so if you actually look through a section through the adrenal gland, the cortex is going to look yellow because it contains a lot of fatty steroid. The medulla is different. Medulla produces catecholamines. It doesn't necessarily process a lot of fat, so it's kind of have a different color, kind of rusty kind of color to it. It's not going to look yellow. All right. Well, we know the adrenal gland has 3 different layers in the cortex. Let's take a closer look at that. Here are the 3 different layers in the cortex. Close-up section through the adrenal gland cortex. There's the cortex right there. And there's the medulla right there. We're interested in the cortex here. There are 3 layers. There's the zona glomerulosa, right there. Zona fasciculata, and there's the zona reticularis. Again, each one of these produces steroids. The zona glomerulosa principally produces aldosterone. The fasciculata, what's that produce? Steroids, yeah, corticosteroids, like cortisol. And how about the reticularis? Androgens, okay, yes. All right, so sex hormones. Aldosterone, of course, comes from the zona glomerulosa, okay, and it's principally going to respond by producing aldosterone in response to angiotensin II. Now, there are a couple of things we need to know about the adrenal gland. Maybe it's not so important to us now, but it'll be important in the future. I mentioned zona glomerulosa, principally controlled by angiotensin II. What controls these other 2 layers?
Negative feedback. Negative feedback loops.
Okay, which ones? What's the hormone that principally controls these 2? Comes from the pituitary gland as well, except the anterior pituitary. ACTH, adrenal corticotropic hormone. Yeah, adrenal corticotropic hormone, that's what controls these 2 other layers. The zona glomerulosa does not respond to ACTH. It responds to angiotensin II. That's important to remember, so that there's no confusion. All right, any questions on this? All right, why don't we take a break here, and then we're going to take a look at exactly how aldosterone affects the